Vector. Physical quantities in physics and science are divided into two categories: scalars and vectors. A scalar quantity has only a magnitude. In other words, it is completely described by its magnitude alone. For example, mass, denoted by m, is a scalar quantity. Time, denoted by t, and electric charge, denoted by q, are also scalars. Scalar quantities are usually represented by lowercase letters. On the other hand, vector quantities have both magnitude and direction. To fully define a vector, both of these properties must be specified. For example, force, denoted by F, is a vector quantity. When a force is applied, both its magnitude and its direction are important. Another example is displacement, denoted by dl. Consider a car moving from a starting point to a destination. The displacement of the car is a vector quantity, and dl represents that displacement. As another example, consider the electric field, denoted by E, between a positive and a negative electric charge. We know that the electric field is directed from the positive charge toward the negative charge. Therefore, like all vector quantities, the electric field has not only a magnitude but also a direction. Now, suppose our information about a vector quantity is incomplete. Imagine a ship or a speedboat floating on the water about to start moving. The only information we have about its velocity is that its speed will be 50 kilometers per hour. If we look at the sea surface from above, we can represent it using a two-dimensional coordinate system, with the boat located at the origin. We know the boat will move at a speed of 50 kilometers per hour. So, after 1 hour, it will be 50 kilometers away from its starting point. However, since we do not know the direction of its motion, we cannot determine its exact position. The boat could travel 50 kilometers along the positive x-axis or the positive y-axis or in any other direction. Therefore, after 1 hour, the only thing we can say is that the boat is 50 kilometers from the origin. In other words, its position must lie somewhere on the circumference of a circle with a radius of 15 kilometers centered at the starting point. The problem here is that we know the magnitude of the vector, but we do not know its direction. Now, suppose we are given one additional piece of information. The boat is moving at 50 kilometers per hour in the negative x direction. With both the magnitude and the direction specified, we can determine the boat's exact position after 1 hour. Now, suppose we represent a vector in a space by A. Every vector has a magnitude, which is a scalar quantity. We usually denote the magnitude of a vector using absolute value bars. So, the magnitude of vector A, written as abs A, simply represents its length. Next, imagine taking a vector with a magnitude of 1 unit and pointing it in exactly the same direction as vector A. The result is called the unit vector of A, and we denote it as A hat A. In physics, and especially in electromagnetics, a unit vector is commonly used to describe a vector whose magnitude is exactly 1 while its direction is identical to that of the original vector A. Using this definition, we can express vector A as the product of its magnitude and its direction. So A would be abs A hat A. This is the standard way we represent vector in physics and electromagnetics. Now, if we rearrange this equation to solve for the unit vector, we obtain A hat A equals to A slash abs A. In other words, to find the unit vector of any vector, simply divide the vector itself by its magnitude. The result is a vector with a magnitude of 1 pointing in the same direction as the original vector.